Alright, good afternoon everyone.
Is that picture of you?
That was a picture of me, yeah. I don't know how old I was.
Change your zoom images always change. Do you just have it set to cycle or something?
No, I just get bored and change it sometimes. But it's purely manual. Alright, I hate to do it, but I think I'm going to have to close the blinds. Because this is...
Right. You changed your spot.
Yeah.
Last term, right when you moved into that house, you were in a different room or something?
I was actually just on the other side of the room. So the view is different.
Oh, I see. How is your new house then?
Oh, it's fantastic. Thank you. Yeah, it's quite a upgrade from my one-bedroom downtown apartment. And it's nice to have space and like everything works and Amazon delivers in like under 24 hours, which is awesome. And all that good sort of stuff. So yeah, it's been a great move, and I'm living with my fiance and daughter, so that's nice. Super bonus. All right, questions? So I'll get your homework graded sometime in the next few days, and I'll post feedback, and then we can talk about it on Monday. Well, there's no class on Monday, actually. Monday's a holiday. Well, that's interesting. And the homework I just posted. Alright, let me change the homework I just posted then. Well, let's see how much we get through today. I think we'll get through enough to do all of the homework, but if there's questions that linger, you can come to office hours on Tuesday. But let's shoot for the homework still being due on Wednesday. But no class Monday, so I'll grade your homework you just turned in the next few days, post some feedback, and then we can go through it Wednesday in class, along with whatever else. All right. Well, let's continue on with propositional logic. So I posted your second homework on Canvas. I did that just before class started, so you have to refresh if you're in Canvas right now. But it's got some follow-up questions on set theory, which should be things that we've already gone over, and then it's got some questions on propositional logic, which is what we started at the end of class on Monday, and we'll continue talking about today. I've had people ask me about being remote versus in person next week, and I don't have an answer yet. I'm going to decide again towards the end of this week. But I just got the first view of case numbers on campus yesterday, and it's not a pretty picture. So I'll seek some guidance from elsewhere. I'll talk to Izad and keep an eye on numbers, and I'll post a decision on Canvas about whether we're going to go back to in-person next week or stick with remote for now. And I'll let you know as soon as a decision is made. Alright, so we ended Monday's class with a definition of a proposition. So let me repeat that. A proposition is a declarative statement that has a truth value. So today is Wednesday, the moon is great of green cheese, the sky is purple, if I wake up early tomorrow, I'll go for a bike ride. These are all declarative statements that have, values of true or false. And so we sometimes use propositional variables. So a propositional variable is a letter that represents a proposition. And so we might say something like, let P be the proposition 1 plus 1 equals 3. Okay, that is a proposition. It's a perfectly well-formed proposition. It's a proposition that happens to be always false. But it is a proposition. It's a declarative statement. It makes a declaration. It declares that this is equal to that. Well, it happens to be false, but that does not have to be true to be a proposition. It's just a declaration, and it has a truth value. So if I say, let P be the proposition, quote, 1 plus 1 equals 3, right? I can use P, and wherever you see that symbol, you understand it means this proposition. All right, so it's like a variable. Okay, I'm going to put a warning on here. Do not ever write something like P equals 1 plus 1 equals 3. That's like totally malformed, right? If I look at this, it looks like P is equal to 1 plus 1, which is 2, but P is also equal to 3, which is different from 2, and this is meaningless, right? So don't ever write P equals to show a proposition. And don't ever write this, right? We don't want to use an equal sign when what we really mean is I am using P as a propositional variable, which means the following proposition. So don't write that either. Stick to this. Let variable be the proposition and then write out the proposition. This is one of these relatively few things I'm going to be very dogmatic about. Right? So if you want to define a proposition to mean the sky is blue, let S be the proposition, quote, the sky is blue. Right? And it may seem like, P equals the sky is blue says the same thing. It doesn't. Okay, so stick to this. That's going to be super important. Don't use the equal sign there.
Why the stickler though? Is it because if we do something later on in code it causes issues?
It's because when we start doing proofs that involve mathematical expressions, if people are writing things like P equals 1 plus 1 equals 2, it leads to mistakenly doing algebraic manipulations on these propositions. And for example, I can't take this proposition and multiply it by 2 or square it. I can't take the proposition the sky is blue and, add 17 to it. But inevitably, if people write something like P equals and a proposition, they start doing arithmetic on P, and it just leads down a really bizarre path that has no benefit to completing a proof. So I'm trying to prevent these missteps down the road. And I'll try to stick to this myself, no matter how rushed I feel or how lazy I am. I'll always try to write this out. Let something be the proposition. But you can yell at me if I slip up on that. All right. So we have a pair of particular propositions that we represent with symbols T and F. And T is a proposition which is simply true, right? And in English, true may not be a declarative statement, but imagine a proposition which is always true no matter what, right? It's just true, right? Is your name Nick? Yes, true. Okay, so that proposition we just represent with T. And the opposite of that, false, we represent with the proposition F. So we can think of those as truth values, if you like. And so this leads to something called propositional calculus, right? And calculus shouldn't be a scary term. It's derived from the Latin word for stone, because stones were used for doing calculations. And so calculus is, doing calculations. Propositional calculus is doing calculations in some sense about propositions, combining propositions, comparing propositions, deriving new propositions from old ones. So this is the subject for the beginning part of this unit, is looking at propositional calculus. And this is a very old subject. In the mid 1800s, we can look at George Boole, from whom we get the term Boolean algebra, right? And George Boole was studying the mathematics of number systems containing two things, 1 and 0, for example, and how to combine these things in different ways, ands and ors, things like that, and was in some sense laying down, the foundations of what we eventually used when we started building computers. But the subject actually goes back quite a bit further to Aristotle, and that's around 300 BC. And among other things, Aristotle studied, these questions of logic and reasoning and human thought, and trying to understand sort of how we construct the arguments and validate the arguments we use when we try to, prove something that we've asserted or disprove something that's been asserted. So this is a very old topic, but it's applicable to some very new areas such as computer science. All right, so throughout the next few minutes, let P, Q, and R be propositions. And I'm not necessarily saying what these are, but they're just going to be propositions. We're just going to have them out there for our general use. And so one thing we like to do is create new propositions from old propositions. And there's a number of ways to do this. So one way is called negation. And we represent negation with this horizontal line with a little hook at the end. Okay, and the hook is important. So I'll draw you a bigger version of this. Horizontal line with a hook at the end. Okay, that's the symbol for negation. And if P is a proposition, the negation of P is also a proposition. And we can read this as saying not P. So in Boolean algebra, we write P with a bar on top of it if P is a Boolean variable. In propositional logic, we write this little negation symbol, this horizontal line with a hook on it, in front of the P. And that means not P, or the negation of P. So now let's give P a particular value. So let P be the proposition. It is sunny. And let's let Q be the proposition 1 plus 1 equals 2. And let F for funny be the proposition 1 plus 1 equals, 95. So we've got a proposition about the weather, and at least right now where I am, it is sunny, so P is true. And we've got a proposition about arithmetic, and in all cases we know of Q is true. And we've got a funny proposition about arithmetic, which says 1 plus 1 equals 95, and F is false. So if I write the negation of P, this is the proposition And in plain speak, this would be the proposition, it is not sunny. That's how we would say this as an English speaker. But in a very kind of rigorous propositional logic sense, this would be the proposition, not it is sunny. But that's kind of a goofy thing to say, right? Unless you're Yoda. Not it is sunny is not how we normally describe it not being sunny. We would just say it's not sunny. So there's a disconnect here, right? Which is English versus logic. The English language is not logical, right? Anybody who's not a native English speaker and has learned English knows English is one of the weirdest languages out there. It's got all these like bizarre rules that don't seem to come from anywhere. And worse, it has rules that work, a lot of the time, but sometimes don't work, and they just don't apply there. Like taking the plural of something by adding s. Well, it doesn't work if you want the plural of deer. And there's no rule you can use to know that. You just have to know it. So when we're talking about propositional logic and we're talking about it in English, there's going to be some tension, right? Because if we try to strictly manipulate a sentence that describes a proposition, we may end up with something bizarre in the sense of English. So we'll generally, if we want to negate P, it is sunny, we'll say, it is not sunny. And we'll understand, that's the negation of it. But I would not say, it is cloudy, because cloudy is not always the opposite of sunny, right? It could be nighttime, and the sky could be clear, right? So it is not sunny is a safe negation of it is sunny. And it could be raining, right? Sometimes it rains when the sun's out. You get a rainbow, yay. So it is not sunny. It could be raining, yeah. And I was fairly imprecise when I said it is sunny. Well, what does that even mean? What is it? I mean, my room is sunny because the window is open. Is it sunny, in Seattle? I don't know. Maybe it's raining up there. Maybe it's cloudy, So we're studying, propositional logic. We're trying to be very rigorous about things, but necessarily we're going to be sloppy sometimes, particularly around matters of the English language. And so if there's confusion about this, just ask, and we'll sort of, try to get a feeling for when we have to be super rigorous, which is when we're doing proofs and we're dealing with changing propositions into other propositions, mainly when we're dealing with propositional variables. But when we're starting a problem or finishing a problem, we're going from English to propositional logic or the other direction, there's sometimes some wiggle room there. So just be aware of that and ask if something's not clear. Alright, so negation of P is just the opposite proposition. And if we want to understand what this does to the truth value of a proposition, because remember, propositions have truth values. This proposition is true or false. This is true or false. This is true or false. Well, this thing is also a proposition, which means this proposition has a truth value. And the truth value of this is related to the truth value of the proposition P. And it turns out if the proposition P is true, then the proposition not P is false. And if P is false, then not P will be true. And that's guaranteed no matter what the actual proposition is. And part of the power of propositional logic is we can make statements about propositions that will be logically correct regardless of what the proposition is. And that's why logic is such a powerful tool for understanding the world and interacting with the world, because it lets us write things that are true, things that are logically correct, without knowing the specifics. And these things that are logically correct, these will be theorems. And we'll learn how to prove these theorems, and once we've proven a theorem, then whatever the particular propositions are, they've got to follow the same theorem. And, you know, as humans, we're emotional creatures. We're creatures with agendas. And sometimes, you know, we want to believe something that's not true. And logic is a way to know whether something is true or not, independent of what we choose to believe. Right? And so this is a really powerful tool. It's a tool that's you know, moved our civilization forward for thousands of years. And it's a tool without which, you know, I fear we're going to go backwards to you know, dark ages. So let's look at what we can do with these propositions. We said if P is true, then not P is false, and if P is false, then not P is true. We can describe that with, guess what, a truth table. You've done Engineering 250, you've seen truth tables before. And we can write a truth table like this. There's the truth table for negation. If P is a proposition that's false, not P is true. If P is a proposition that's true, not P is false. And again, the beauty here is that it does not matter what P is. It could be this proposition, that proposition, that proposition. It does not matter. If P is false, not P is true. And yeah, so someone points out in chat, the outcome of a logical deduction is only as true as the propositions and assumptions. So when we make a theorem, it's usually going to say, you know, given this and this and this, we can conclude that, right? Well, if you're not given this and this and this, that theorem has no usefulness in concluding that is true or that is false, right? These are going to be very specific. And so knowing when a theorem is applicable to a situation, right, is often part of the challenge too. And so this will be, you know, some of the work we do in going between an English statement of a problem, a written statement of a problem, into a statement in the language of propositional logic. And we'll see some examples of this coming up. Theorems and also what we call fallacies. All right, so here's the truth table for negation, and it looks just like, you know, the truth table for an inverter or a not or a complement in Boolean algebra. False we think of as a 0, true as a 1, 0, 1, 1, 0. We've seen that before. All right, so negation is one way we can create new propositions from old propositions. And just for specifics, you know, the negation of P is the proposition that it's not sunny. Well, that's false right now, because to me the sun is out. Not Q would be the proposition 1 plus 1 is not equal to 2. That is false. Not F would be the proposition 1 plus 1 is not equal to 95. That is true. Right? So F is false, not F is true. All right. Conjunction. So if we have two propositions, P and Q, we can write P caret Q. And we think of this as P and Q. And this is conjunction. And this is a new proposition. P is a proposition, Q is a proposition. The conjunction of P with Q is a third proposition. And in English it means that P is true and also that Q is true. So over here on our original set, P and Q would be the proposition, it is sunny and 1 plus 1 equals 2. And that proposition turns out to be true. Q and F is the proposition that 1 plus 1 equals 2 and 1 plus 1 equals 95. And that is false.
Can we not use the and symbol?
What's the and symbol?
Or ampersand?
Oh, no. No, let's use the caret.
Okay, interesting.
Yeah. And the hooked horizontal line for negation. But you can think of it as an ampersand if you like that notation, or you can think of it as the word and. But when we do proofs and stuff, we're going to use this notation. So that's the conjunction, and we can describe what conjunction does to two propositions. So if we have two propositions P and Q, there's exactly four possibilities. They're both false, one of them is true two different ways, or they're both true. And based on that, the new proposition P and Q will be true in only one case, which is where P is true and Q is true. That's kind of what it means when we say P and Q. So conjunction is like a good old AND operator from Boolean logic, Engineering 250. Alright, next is disjunction. So we can say P or Q and that's called a V, but it's not the letter V, it's a upside down caret. This is disjunction. And it says P or Q is true. And so P or Q, in this case, is the proposition, it is sunny or 1 plus 1 equals 2. Well, it turns out this proposition is always going to be true, whether it's sunny or not, because 1 plus 1 is always equal to 2. So P or Q is always going to turn out to be true. Q or F is the proposition 1 plus 1 equals 2 or 1 plus 1 equals 95. That's going to be true all the time also. Even though F is a really funny proposition that is always false, right? Q or F turns out to be true. And so we can write a truth table for disjunction, and it looks just like the truth table for an OR. If Q is true, or if P is true, or if both of them are true, then this disjunction of P and Q turns out to be true. And it turns out to be false only when P and Q are both false. Alright, sometimes, not too often surprisingly, we'll also have an exclusive OR. So that's an OR with a circle around it. And that's the same symbol from Engineering 250. And that means P is true or Q is true, but not both. So it looks like a regular disjunction, except if both P and Q are true, then the XOR is false. Alright, so this is presumably repeat for everybody because, you know, this is CSE120 and this is also Engineering 250. It's one chapter in 120 and it's pretty much all of 250. So where it goes beyond what we do in 250 is when we start talking about conditional statements. So again, imagine P and Q are propositions. I'm going to show you a new proposition, which is P arrow Q. So P arrow Q is the proposition if P, then Q. It's an if statement, but it's also a proposition. It's a declarative statement. This in itself is a proposition, which says if something, then something else. And we call P the hypothesis, and we call Q the conclusion. And so P followed by an arrow followed by a Q is the proposition if P then Q. So for example, with this set of propositions, P arrow Q, is the proposition, the declarative statement, if it is sunny, then 1 plus 1 equals 2. Q arrow P would be the declarative statement, if 1 plus 1 equals 2, then it is sunny. Q arrow F is the proposition, if 1 plus 1 equals 2, then 1 plus 1 equals 95. Does everybody get the idea that those are all declarative statements? Some of them are nonsensical, but they're all propositions. Propositions don't have to be reasonable. They just have to be a declaration that's either true or false.
Makes sense to me.
Okay. So we can create new propositions out of old by doing a disjunction, a conjunction, by doing negation, or by putting them together in this conditional statement. So again, this is called a conditional. So if P, then Q.
Is Q another proposition?
P is a proposition, Q is a proposition, and then if P, then Q is another proposition.
Okay. Would you like to turn on for a second?
No, I took an attendance screenshot because we're missing like 40% of the class. So I just wanted to record who was here. So when I do that, the screen gets dark.
Should have graded attendance.
Yeah, well, yeah. There's rewards.
Well, it would have been in person, but it's not.
Yeah. Yeah, it's mostly, you know, if someone's coming in the 11th hour and is really struggling with something and they've been coming to class, right? Then I know, you know, what they've heard in lecture and I can probably help them. If someone comes in and they're really struggling with something and they haven't been in class, right, then I have no idea, you know, what they know, but I might have to go back to, you know, square one and reteach the class, and I usually can't do that. So I just kind of like to know who's coming into class and who's not. But it doesn't go into your grade directly, so. Alright, so here's a new proposition, if P then Q. Alright? And so let me give you some other examples. Let S be the proposition. It is sunny. Let R be the proposition. I go for a run. That's one proposition, says it's sunny. This is a second proposition which says I go for a run. Here's a third proposition which says if it is sunny, then I go for a run. Let me make this a little better English. I'll go for a run after class. I'll try to be at least somewhat proper in English. So this is the proposition, if it is sunny, then I'll go for a run after class. And if you want to expand this, really, you just put an if in front of S and the then in front of R and just plug in what S and R say. If it is sunny, then I'll go for a run after class. So that's the third proposition. And so we can phrase this as if S, then R. But again, you know, relaxed protocols for English, sometimes you might just say if S, comma R. If it's sunny, I'll go for a run after class. Sometimes you don't actually say the word then. right? So why use many words when a few will do the trick? Here's another version. S is sufficient for R. What does this mean? Being sunny is sufficient for me to go for a run after class. So we're getting into the sloppiness of English here, right? But it being sunny is sufficient for me to go for a run after class. I don't need to feel good. I don't need to have drank my energy drink. I don't need to have a friend call me up and say, let's go for a run. A sufficient condition for me to go for a run after class is simply, it is sunny. How do I know that? Because I've stated the proposition. If it's sunny, then I go for a run after class. So this is equivalent to, it being sunny is a sufficient condition for me to go for a run. R if S. I'll go for a run after class if it is sunny. Well, that's also equivalent. R unless not S. I will go for a run after class unless it is not sunny. And so there's lots of ways in English that we can phrase the same proposition. And when we're starting with, a description of a problem where we're asked to analyze it using propositional logic, sometimes a big part of the challenge is knowing how to translate it into, the P's and Q's and R's and arrows and carrots of propositional logic. And so there's homework questions that delve into all these different aspects and challenges to get some practice. All right, so here comes a really weird thing. The truth table of a conditional statement. So suppose P and Q are propositions, and there's 4 possibilities. And we want to look for each of these 4 possibilities, what is the truth of this conditional statement if P then Q? And suppose that P, our hypothesis, is true, and suppose Q, the conclusion, is also true, and we make the claim if P then Q. Well, if P is true and Q is true, is this if statement itself also true?
Yes.
Yeah. Because the only thing the statement claims is that if P is true, then Q is true. And in this case, hey, P is true and Q is true also. So yeah, here this P implies Q, this if-then statement is definitely true. So what about this third case? Suppose P is true and Q is false.
True. It would still be true though, wouldn't it?
Well, let's see.
P is true.
So suppose, if it is sunny, then I'll go for a run after class. So suppose it's sunny and I don't go for a run after class. Is this if-then statement true or false in that case?
It'd be false because it breaks.
It's false because it breaks, right? This statement says if it's sunny, I'll go for a run. But if in fact it's sunny and I don't go for a run, well, this if-then statement is a bunch of baloney. It's false. So those two kind of work, the way that our intuition might suggest they work. But things get really interesting with these first 2 cases. And it turns out that for both of these cases, the conditional will end up being true. And that probably rubs us the wrong way.
I mean, the first one makes sense, but the second one, not so much.
Yeah. So let's
Yeah, that second one doesn't make much sense.
let's think about this a few different ways. So first of all, let's suppose that, you know, if it's sunny, then I go run. Let's just suppose that this conditional statement is absolutely true. This is etched in stone. It's buried in my DNA. Anytime the sun comes out, I'm going to go run. Okay, let's just for a moment believe that that's true. It's not. I wish it was. But let's believe that that's absolutely true. This first row is saying it's not sunny and I didn't go for a run. Does that suddenly make this thing false?
No, it would make it true.
It doesn't make it true either, but it doesn't make it false. It doesn't violate it. It says nothing about this. All that this says is if it's sunny, then I'll go for a run. Well, if it's not sunny and I don't go for a run, that's not a problem. I haven't violated, you know, the coding in my DNA.
It doesn't say that you only go running if it's sunny.
Exactly. And so in the second case, you know, it's not sunny, but I decide to go for a run because guess what? I go run every single day no matter what the weather's doing. Well, that doesn't violate this because, again, it doesn't say only if it's sunny will I go for a run. And so this conditional would turn out to be true in all cases except this third one, where it's sunny, but I decide I'm going to sit around and eat some ice cream instead. Right? Well, now that proposition is false.
Sounds like me.
Yay! Now I want ice cream. Alright, so let me try a different pair of propositions and give you a different way to look at this. And then I'm going to say, you know, this is the way it is, just take my word for it. So let me give you a different pair of propositions and see where this leads. Let P be the proposition n, whatever n is, some number that I'm thinking of, n is bigger than 1,000. And let Q be the proposition n is bigger than 5. And let's think about the truth table. For if P, then Q. Well, forget the truth table for a moment. Just think about if P, then Q. If n is bigger than 1,000, then n is bigger than 5. Is that statement always true?
Yes.
Yeah, I mean, thinking about just integers, for example. If I think of some integer n and it's bigger than 1,000, it's definitely bigger than 5. Right? So this proposition is absolutely true. Right? Any n I think of, if P then Q turns out to be true. Okay, so let's pick an example. Suppose I say n equals, 2,000. Well, P is the proposition that n is bigger than 1,000. P is true. Q is the proposition n is bigger than 5. Q is also true. So P and Q are both true. And this says, if n is bigger than 1,000, n is bigger than 5. Well, we know that's true. Right? This is always true. Well, suppose I happen to pick a value of n which is equal to 0. Well, P is false and Q is false. But we can't suddenly say, sometimes this isn't true. Well, no, this is a true statement. If n is bigger than 1,000, it's bigger than 5. If I happen to pick a value of n where both P and Q are false, that doesn't change the fact that this if-then statement is absolutely true. And if I happen to think of a value like n equals 10, well, P, n is bigger than 1,000, that's false. But Q, n is bigger than 5, that's true. But still, it doesn't matter what value of n I pick. For any value of n I pick, if P, then Q is a true statement. So with those particular propositions, maybe you can see why these three rows have to have a value of true for the conditional statement. But then we got this little oddball case here. And I've told you that the conditional statement will be false. But is there any value of n where p is going to be true and q is going to be false?
Probably not.
Can you think of a number bigger than 1,000 but not bigger than 5? Probably not. So if it turned out that p was true and q was false, this conditional would fail. But there's no values of n where these are the truth values of p and q. So this never occurs, right? And this is why if p then q is true for all possible values of n. Because for every possible value of n, you're in either this row or this row or this row. So this is one of those many points where I'm going to say, you know, think about this and then stop thinking about it. And maybe come back and think about it more later. But it can get us all twisted up, wondering, you know, why this is true and why this is true. And how this can be false, but this statement can always be true. And the more we work with this, the more it will sort of start to make sense. And after it makes, you know, a certain amount of sense, suddenly it'll make no sense. And then we'll think about it some more and it'll start to make sense again. And all we need to know when we're doing proofs or homework problems or exam questions really is, you know, in this case, the truth table for a conditional statement. And so even if it works against our intuition sometimes, right, as long as we know what the truth table is for a conditional, we can use that and not have to, you know, use our intuition to prove something, right? So remember this, put this on your note sheet, come back to this when you're trying to actually do a proof or a problem. But it's useful to think sometimes about what this actually means. And I'll give you a bizarre example. Well, a seemingly bizarre example. It may not be as bizarre. But let P be the proposition 1 plus 1 equals 3. Let Q be the proposition I am the Queen of England. Alright, P arrow Q is the proposition if 1 plus 1 equals 3, then I am the Queen of England. Well, P turns out to be false, and if P is false, it doesn't matter what the value of Q is. If P, then Q is always true. So this proposition is absolutely true. If 1 plus 1 equals 3, then I am the Queen of England. That is a true proposition. And that can seem absurd. But from a point of view of propositional logic, this is a true proposition. And it's true precisely because the hypothesis is always false. The fact that the conclusion is false has no bearing on the truth value of the conditional statement. So we'll bump into this sometimes, and that may be jarring because it's you know, something ridiculous and something ridiculous, but when we put them together in an if-then, the statement turns out to be true. So again, come back to the truth table. False, false, conditional is true. Alright, so we'll mess with those more as we go through this. But let's look at other ways that we can derive propositions from other propositions. So if we have a conditional statement, there's 3 other propositions we can derive. The first is called the converse. So given the proposition, if P then Q, The converse is another proposition which says if Q, then P. So if you start with a proposition if P, then Q, we can derive a new proposition which says if Q, then P. That's called the converse of the original. We can derive a second proposition which is the inverse, which is the proposition if not P, then not Q. And the third proposition we can derive from the original is the contrapositive, which is the converse of the inverse. So it's if not Q, then not P.
Did you say counterpositive or that's
Contra.
Contra.
Yeah, contrapositive, like contra dance or Iran Contra.
Of the game.
Yeah. All right. So let's look at the the truth value of these things. So let me pick some propositions. So I have propositions P and Q. So let P be the proposition. I win the lottery. And let Q be the proposition I cancel a class next week. Okay, if P then Q, that's the proposition. If I win the lottery, then I cancel class next week. I wouldn't do that to you. But, let's imagine that, I win the lottery, so I'm going to go on a trip or something. So if I win the lottery, then I cancel class next week. That's what this statement says. The converse says, if I cancel class next week, then I won the lottery. And there's a couple of things to say here. First of all, this is not cause and effect. So let me just change this to if I won the lottery, then I cancel class next week. So if I cancel class next week, then I won the lottery. And it's absolutely not saying, hey, if I cancel classes, I'm going to win the lottery. It's not a cause and effect kind of thing, right? But the converse is saying, if I cancel class next week, then I won the lottery. Well, suppose that if P, then Q is true. If I won the lottery, then I cancel class next week. What can we say about if Q, then P? If I cancel class next week, I won the lottery. Is that guaranteed to be true?
No.
No. Maybe I get sick next week, and that's why I cancel class. So this is not equivalent to if P, then Q. This is a different proposition. It could have the same truth values, but it might not. It's not saying the same thing. The inverse is saying, if I don't win the lottery, then I will not cancel class. Well, that may not be the same thing. That may not be true, because again, maybe I get sick next week. Well, I didn't win the lottery, but maybe I will cancel class. So this is also not equivalent to if P, then Q. But this, the contrapositive, says, if I do not cancel class, then I did not win the lottery. And that's actually logically exactly the same as if I win the lottery, then I cancel class next week. All right, so imagine it's a fixed fact if I win the lottery, I'll cancel class. This is saying if I don't cancel class, I didn't win the lottery. Well, that's exactly the same thing. Because if I don't cancel class, I could not have won the lottery, because if I win the lottery, I'm going to cancel class. So this is actually equivalent to if P then Q. And so we can write the following. P arrow Q is equivalent to, not Q, arrow, not P. And this symbol up here means equivalent. Equivalent meaning has exactly the same truth value in all possible cases. So the same truth table, if you like. Right? And this non-equivalence is really important, and it's something that oftentimes we don't understand. So if I rob a bank, then I'm wearing a mask, right? Because you put a bandana over your mask so you go in so the cameras don't record your picture. So if I'm a bank robber, then I wear a mask. Well, the converse says if I wear a mask, then I'm a bank robber. Well, no, that's not true. I'm on campus and I'm required to wear a mask. So this is not a logically true statement, whereas this might be a perfectly logically true statement in all cases. If I'm going to rob a bank, I'm going to wear a mask. If I'm wearing a mask, then I'm going to go rob a bank. Well, that doesn't follow. This says if I don't wear a mask, I'm not going to rob a bank. Well, that may not be true. Sorry, this says if I rob a bank, I'm going to wear a mask. It says if I'm not robbing a bank, I'm not going to wear a mask. Well, that's not true either, because maybe I'm just on campus and I need to wear a mask. But the contrapositive says if I'm not wearing a mask, then I'm not going to rob a bank. Well, that is true. Supposing that it's true that if I'm going to rob a bank, I'll wear a mask. Well, if I'm not wearing a mask, I'm not going to rob a bank. So these things are equivalent. These are not, these are not. Alright, biconditionals. So this is a plain old conditional. It says if P then Q. If we also know if Q then P, that's what we call a biconditional. This basically says if P then Q, and if Q then P. Well, this means if P is true, Q is true. If Q is true, P is true. If Q is false, right, then P must be false, because if P was true, Q would be true. And if P is false, then Q must be false, because if Q was true, P would be true. So this is the same thing as P if and only if Q, which we sometimes write P if with two F's, P if and only if Q, or we write it as a two-headed arrow, P if and only if Q. Or sometimes we say P is necessary and sufficient for Q, or Q is necessary and sufficient for P. Well, let's just declare that IFF is a real word, and we'll just use it in casual speech, because I love that word. Alright, so let's look at the truth tables for these. P, Q. So both false, one of them true in either order, both of them true. If P, then Q. So that's true except when the hypothesis is true and the conclusion is false. If Q, then P will be true in all cases except when the hypothesis is true and the conclusion is false. So this will be false here and true in all other cases. And then if we take the conjunction of those last two columns, this is P if and only if Q. And the conjunction of these two columns will be true, false, false, true. And you can see that, P and Q are either both true or both false. As long as that's the case, then this biconditional is true. And so this is also a way of saying that P and Q have the same truth value. They vary together. They're either both true or they're both false. And by the way, if we do the exclusive OR, and we complement that, we get the same truth values as the biconditional. So a biconditional, an if and only if, is really just an exclusive NOR. I don't know what that means, but that's something to think about. The good old XOR, XNOR operations from Engineering 250, well, the exclusive NOR is logically equivalent to an if and only if statement. And that's probably a little bizarre to think about. So that's a good place for a break. And let's come back at 5.25 minutes. We'll come back and we will we'll continue looking at truth tables, and then we'll start talking about propositional equivalence in more detail. Alright, so take a break, stretch your legs, come back in 5 minutes. Alright, there's a concept of propositional equivalence, which is basically saying that two propositions have the same value in all cases. And you know, biconditional equivalence, same idea. So for example, you know, if P and Q are propositions, P or Q, Q or P, these are always going to have the same truth values. Right? So I could write P or Q is equivalent to Q or P. Because the way disjunction works, it doesn't matter in what order we talk about two propositions. But sometimes we may find that there's a proposition which is always logically equivalent to true. And if we have a proposition which is always equivalent to true, we call that a tautology. So for example, the proposition P or not P. This proposition is always true. Doesn't matter what P is, it doesn't matter what the truth value of P is. The proposition P or not P is always true.
Is that pronounced tautology?
I think it's tautology, like tautology.
Yeah, it's tautology.
Okay.
Thank you.
So we can see the truth value of this expression with the truth table. P is either false or true. Not P will be the opposite, true or false. And the disjunction of those, well, false or true is true, true or false is true. So regardless of the value of P, this statement right here is always true. So this is a tautology. What does it mean? Hey, your name is Nick or your name is not Nick. That statement is true. Right? Your name is Nick or your name is not Nick. So that's a tautology. A contradiction is a statement that's logically equivalent to false. And here's a simple example of a contradiction. P and not P. That is always false. Doesn't matter what P is. If P is the proposition 1 plus 1 equals 2, this says 1 plus 1 equals 2 and 1 plus 1 is not equal to 2. That's a false statement. If P is the proposition, my name is Nick, and my name is not Nick, that's a false proposition. I am the Queen of England, and I am not the Queen of England. That is a false proposition. So this is logically equivalent to false. And any proposition logically equivalent to false is called a contradiction. The third possibility is a contingency, and a contingency may be true or false depending on the values of other propositions, for example, P or Q. Well, this is not always true or always false. It depends on the values of P and Q. If P happens to be true, this will be true. If P and Q are both false, this will be false. So this is a contingency. And most propositions we work with will be contingent. But sometimes we'll find a contradiction and be able to make good use of that, or sometimes we're trying to show that something is a tautology. Alright, so those are some definitions and some concepts. And these are closely related to identities. So we can start writing down identities related to propositions. And these things that we write are going to be always true. These statements that we're about to write. For example, if P is some proposition, P and true is logically equivalent to P. And this is absolutely true no matter what the proposition P is. So if I take P and I AND it with true, I get P. And if I take P and I OR it with false, that's also equivalent to P. And again, it doesn't matter what the proposition P is. So P could be the proposition 1 plus 1 equals 2. 1 plus 1 equals 2 and true, well, that's going to be true. But it's going to be the same, it's going to be true because 1 plus 1 equals 2 is true. If P is the proposition 1 plus 1 equals 3, P and T, 1 plus 1 equals 3 and true, well, that's false. And P itself is false. And same thing with doing a disjunction with false. So this is an identity. So is this. P and false is false. P or true is true. P or P is equivalent to P. P and P is equivalent to P. The negation of P is also equivalent to P. And do these look familiar from other courses?
Yeah.
Yeah. Engineering 250, right? So this is the Boolean algebra we developed in 250 and to some degree in 120. And we use ones and zeros instead of true and false, and we use, you know, dots and plus signs instead of carets and V's. But it's the same relationship among these things. And we have all the good old favorites. P or Q is logically equivalent to Q or P. P and Q is logically equivalent to Q and P, so that's commutivity. P or Q or R is logically equivalent to P or Q done first and then ORed with R, and so on. That's associativity. And we have distribution. P or the proposition Q and R is logically equivalent to P or Q ANDed with the proposition P or R. So we can distribute the OR over the ANDs, right? That's like algebraic distribution. And the all-time crowd pleaser. The negation of P or Q is logically equivalent to the negation of P ANDed with the negation of Q. Somebody tell me the name of that theorem. biggest crowd pleaser? At least tell me in chat. Not familiar?
What is if?
We did it in set theory.
Oh, you're just multiplying out the,
Remember this from 250?
oh, yeah, okay.
Yeah, the Die Morning theory, there we go. De Morgan's theorem. So De Morgan's theorem works for propositions as well. Alright, and let me mention a few others, and I'll point you to a place in the book where you can find all of these. So P and not P is equivalent to false. I think we did that one already. Nope, we didn't. So P and not P is equivalent to false, and P or not P is equivalent to true. I think we did those for contradictions and tautologies. But here's a useful one. P or P and Q. This is logically equivalent to P. The Q gets absorbed and goes away. And this is a really useful identity to know, because if we have an expression like this, we can toss the Q away. We can simplify this whole thing down to just P. Well, how do we know that's an identity? We can prove it using a truth table. So let's do that. Let's write out P and Q. False, 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 true, true, false, true, true. And let's write down this second expression, P and Q, so they're conjunction. And this is false, 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 true. And now let's write down P or P and Q. So let's take the disjunction of this column and this column. So false or false is false. False or false is false. True or false is true. True or true is true. And then we make the observation that the truth value of this expression is always the same as the truth value of that expression. They are either both false or they're both true. That's what it means when we say this expression is equivalent to that expression. It means they always have the same truth values. So there's a proof through a truth table that this is equivalent to that. Logically, why does this work? Well, this is basically saying, I want this expression to be true if P is true, or if P and Q are both true. Right? P is true, or P and Q are both true. Well, if P is true, this whole thing is going to be true. If P is false, this is going to be false, which means P or that is going to be false. And so if P is true, this is true. If P is false, this is false. So this is equivalent to P. Meaning equivalent in truth value to the truth value of P. Alright, so in your text, if you go down to page 58 in the PDF, there's these basic logical laws. So commutative laws, right? You can switch the order of two things when you do conjunction or disjunction. Associative laws, you can move the parentheses. Distributive laws, these are called identity laws. Oring with a 0, ending with a 1 doesn't change the value. Negation laws, ending with the complement or oring with the complement gives you either false or true. and so on and so forth. There's De Morgan's, there's involution, which is double negation, there's absorption that we just talked about. So here's a table on page 58 that shows you the basic identities that we're going to use. This is going to be our second favorite table for this unit. Our favorite's going to be on the next page, common implications and equivalences. And we're going to use these two pages a lot. And we're going to use them a lot in proofs. So the ones of these rules that you don't have memorized over the next few weeks, you definitely want to put down on your note sheet for the midterm and for the final. But what we can do is we can use these identities to prove that certain things are equivalent to other things. And the fundamental proof that we're going to do in this course is basically showing equivalences between propositions. So let's do an example of a proof like this. So I want to prove the following unusual equivalence. All right. So this is our first of many proofs in this course. And proofs can trip people up sometimes, and they take some getting used to for sure. But if we keep a few things straight up front, it will increase our chances of having a pleasant experience with proofs. So a few things up front. First of all, how we do a proof is really the most important thing. You're going to see, questions on homework or on tests that ask you to prove things, and the person writing the question already knows this thing is true. So the goal is not necessarily, to prove something that's never been proven. It's an exercise to see if you know how to construct a proof. And so the way you construct a proof, the way you put it together, the way you choose the pieces of your proof, that's where the real money is, okay? Slopping some things down on paper and scribbling some notes and then coming down to the conclusion doesn't get you anything, right? The whole exercise here is how we construct a proof. Getting good at, writing each statement, making sure each statement is a proposition, making sure each statement follows from the previous, that we justify each statement. All these things that we're going to do very, very carefully, right? That's what we're after when you try to do a proof on your own. All right, so how we go about doing the proof, that's what we're really concentrating on. It's not the conclusion of the proof that's the most valuable thing here. It's the process we go through. So that's one thing to keep in mind. And so I want to go about proving this using laws of logic, using identities, and I'm going to structure it in a very specific way. We're going to write a series of propositions. And each proposition is going to be absolutely true based on the propositions we've written above it. And we're going to write a justification for each proposition next to it. And we're going to number our propositions starting with 1. All right, so here's another thing, and this is a little tricky to describe in general, but if you accidentally do this, it'll be really easy to say why what you did was not the right thing to do. So I'll just phrase this imperfectly as, don't just manipulate both sides. And you've probably heard this in math classes, maybe in geometry or some other class where you did proofs. Suppose, you know, you want to prove n plus 1 squared equals n squared plus 2n plus 1. Pretend this is an algebra course, okay? We want to prove that this is equal to that. Well, the proper way to do that is to take this expression and somehow transform it. Write this as n plus 1 times n plus 1. And then multiply those together using FOIL. And then combine your two n terms together. And then rearrange your terms and show that this is equal to n squared plus 2n plus 1. But here's something that is not a valid proof, right? Let's say x times n plus 1 squared equals x times n squared plus 2n plus 1. X times n plus 1 times n plus 1 equals xn squared plus x times 2n plus x. Let x equal 0. 0 is equal to 0. Hey, I'm done. I proved it. Okay. Is this a valid proof that this is equal to that? What do you think?
No, because it could fail for other values as well.
Yeah. I mean, if this was a valid way to prove something, I could say prove 1 equals 2. Well, let's see. 1 equals 2. 1 times 0 equals 2 times 0. 0 equals 0. Bang, we're done. Yeah, 1 equals 2. Give me a quarter. Right? That's not a valid proof. What we've proven here is if 1 equals 2, then 0 equals 0. Well, that's totally true. But if you do this and you turn it in, what you're claiming is since 0 equals 0, then 1 equals 2. You've proven the converse of what you wanted to prove. You proved if this is true, then that is true. Sorry, you proved if this is true, then that is true. That does not tell you that if this is true, that is true. So let me go through this and show you how you would like to go about doing this proof. And keep that in mind. And if you accidentally do what I just described, right, then I'll make comments to that effect, and we can talk about it in detail. And it's easier with specifics. And this looks so silly, nobody would actually claim 1 equals 2 because of this, right? But that's basically what's at work if you accidentally manipulate both sides. All right. So this is a puzzle game. One of the things about proofs is there's no sort of algorithm you can follow that says, hey, do these things and at the end you'll be done. Okay, it's very much like physics homework in that sense. There's no procedure you can follow so that when you're given a physics problem, do these steps and you'll get the answer. It does not exist, right? You have to do enough problems, you have to see enough problems, you have to try enough problems that eventually, you know, you see an inclined plane with a cylinder and some vectors drawn, and your experience will say, oh, I should take those vectors and reorient them so that one of them is parallel to the inclined plane, and I'll do some sines and cosines to transform gravity and so on, right? But it comes from experience, okay? Exactly the same with proofs. There's nothing we can do with this problem that says, oh, first I should use De Morgan's theorem, and then I should do propositional equivalence, and so on and so forth. It's a trial and error thing. So you keep these in mind, or, you know, on a sheet of paper next to you, and you look at them, and you look at what you're trying to work with. We've got two things negated that we're anding. We've got an or with something and something in parentheses, and we're negating that or. And maybe that makes you think De Morgan's theorem, you know, because De Morgan is always about negations and conjunctions and disjunctions. So we could do something like this. We could say the negation of P or negation P and Q is equivalent to, well, if we use De Morgan's theorem, the negation of this thing ORed with this thing is the same as the conjunction of the first thing negated and the second thing negated. So I've just sort of blindly applied De Morgan's theorem, and I said, let's take this first thing, negate it, let's take the second thing, negate it, and let's take their conjunction. And that should be equivalent to the negation of the disjunction. Alright, I'm going to number this as statement 1, and my reason is De Morgan's theorem. Doesn't matter what P and Q are. Doesn't matter what I was asked to prove. All I've done is made one statement. This is equivalent to that. And I can justify that statement by saying this is De Morgan's theorem. And the goal is, if I show this proof to somebody, because I'm trying to convince them of something, when they look at this first statement, they should see that this is true. If they don't, they can say, oh, De Morgan's theorem. Oh yeah, De Morgan's theorem says that's equivalent to that. So presenting a proof, you're trying to convince the reader of something that you've come to the conclusion. And you can assume that the reader understands propositional logic. They know what De Morgan's theorem is. They know what commutativity is. But they don't know why this is equivalent to that. That's what you're trying to prove to them. So sometimes it's a little tricky to figure out how much detail to put in, right? I'm not going to prove De Morgan's theorem, but I'm going to use it. I'm going to say this is equivalent to this. All right. Well, I'm also going to try to do some transformation on this side. So I might do something like this. Right? I'm going to look at this piece of my expression. And that kind of screams out for De Morgan's theorem also. Right? This kind of looks like it's saying, the negation of something ended with something. Well, this is equivalent to the negation of the first thing disjuncted with the negation of the second thing. And that's also De Morgan's theorem. Alright, is there anything I could do to this expression maybe to simplify it? I'm just looking at this right-hand side.
Involution not P.
Yeah, so involution or double negation, not P is the same thing as P. Right? And that's on our list of identities. The double negation of P is equivalent to P. So the book uses double arrows sometimes for equivalence, or biconditional equivalence. So I'm going to write another statement here, and I'm going to say the negation of P, ORed with the negation of Q, is logically equivalent to P ORed with the negation of Q. And the reason for that is involution. So we're making little steps from one statement to the next, and we're justifying each step. Alright, well now I'm going to go back up here to this second statement I had, and I'm going to write the following. Not P, ended with the negation of not P or and Q, is logically equivalent to not P, ended with, well, this negation of not P and Q, I've shown that that's equivalent to not P or not Q. And I've shown not P or not Q is equivalent to P or not Q. Well, let me throw in one other step here. Let me put steps 2 and 3 together. And let me say the negation of P and Q. Well, that's equivalent to this thing, and I show that this thing is equivalent to P or not Q. And so this is equivalent to that, that's equivalent to this other thing, so this is equivalent to the other thing. And that's something we call a transitive property, applied to statements 2 and 3. So if A is equivalent to B and B is equivalent to C, then A is equivalent to C. And that's usually called transitive. So now I've shown that this thing that I underlined here is equivalent to P or not Q. I'm just going to plug this in place of P or not Q. Or not P or Q. So I'm going to say the negation of P or not P and Q is equivalent to negation of P ANDed with, but instead of this expression here, I'm going to put in this expression, P or not Q. And this is just substituting 4 into 1. So I just replaced this part of expression 1, equivalence 1, with this. And that tells me this is equivalent to this. So you get the idea of what we're doing here, ignoring the specifics.
Yeah, like doing algebra.
We're just doing algebra, right? It happens to be propositional algebra, or maybe a version of Boolean algebra. So the specifics are trial and error, and it's a matter of knowing what the different identities are, and sometimes having an insight, or sometimes just blindly trying different identities and seeing if something like makes progress, gets you closer to where you're trying to go. So we're trying to show that this thing is equivalent to this. And we've shown that it's equivalent to this. Well, this is closer. We've got our not P right here. We've got a P or not Q over here. So we're getting pretty close. Let's see what we can do with this. And we have distributive laws, which basically say if we have something ANDed with an OR, we can expand that into two ANDs ORed together. So P and Q or R is the same as P and Q or P and R. And if you think of this as like multiplication and addition, A times B plus C is the same as A times B plus A times C. And it doesn't matter, if I'm trying to do something with negation of P, I can just put negation of P in every time that I see this. Negation of P ANDed all of this will be equivalent to negation of P ANDed with Q, or the negation of P ANDed with R. These are just boxes. We can fill them in with whatever we want. So if we use the distributive law on this statement, this is equivalent to not P and P, or not P and not Q. That's the distributive law. Well, can we do anything to clean up this expression?
Not P and or rather, not P and P is always false.
Not P and P is always false. That's the negation law. Not P and P is equivalent to 0 or false.
And then false forward with anything is just the same.
Mm-hmm.
Mm-hmm.
Got it. So that's the negation law applied to 6. So this is equivalent to false or that. And then we have this other law that says if we take false and we OR it with an expression, we just get back the expression. If we have a proposition P ORed with false, we just get P. That's the identity law. So false ORed with this will be the original proposition. Well, technically, and since we're being like really long-winded about this, let me stick to that. The identity law says a proposition ORed with false is the same as a proposition. But we don't have a proposition ORed with false. We have false ORed with a proposition. So the way the identity law is written on page 58, it does not apply to this proposition. But we have another law called commutativity, which says this is equivalent to not P and not Q, ORed with false. And that's applying the commutativity law to part of statement 7. And now, not P ANDed with P or not Q is equivalent, and we have the identity law, which says a proposition ORed with false is equivalent to the proposition. So this ORed with false will be the same thing as not P and not Q. That's the identity law applied to proposition 8. I'll throw in parentheses for clarity. And guess what? We just proved that this is equivalent to that, this is equivalent to this. We did all these things. We just proved that this proposition is equivalent to that proposition. Well, what the heck were we trying to do? We were trying to prove that what were we trying to do? Whoa, took a wrong turn somewhere.
No, right. We're trying to prove that not quantity of P or the quantity of not P and Q is equal to not P and not Q, right?
Yeah.
Which we did in step 9.
Yeah, I misfired somewhere. So we're trying to show not P or...
You lost me after 4, I think.
Yeah, I think I lost myself. Not P or this thing is equivalent to this. Okay. So yeah, we got one more step to do. So we knew that not P or not P and Q is equivalent to this expression, and we just showed that this expression is equivalent to this. So this is equivalent to that, that's equivalent to this other thing. So one more transitive law, we can say that negation of P or not P and Q is equivalent to not P ANDed with not Q, and that's transitivity using expressions 5 and 9. And so now the thing that we've shown is the thing that we were trying to show. We were trying to show that this expression was equivalent to that expression. Well, we just demonstrated that. And once you've demonstrated the thing that you're trying to prove, you can write the letters QED, which is a Latin phrase meaning which is what we were trying to prove, which is what we were asked to demonstrate. And that marks the end of your proof. Alright, so at this stage of things, I'm not too worried about, how did we get from here to here while we used involution? How did we get from here to here and so on? What I want you to see is the style in which we did this. Right? We wrote a series of propositions. Each of these is a proposition. This is the proposition that this expression is equivalent to that. So each statement we wrote is a proposition, and each proposition must be true. And the reason it's true has to be justified to the right of it. And we number these propositions because sometimes what proves that a proposition is true is related to the fact that there's other propositions that we've written that are true. For example, if this is true and this is true, then we know that this is equivalent to that, so this fourth statement is true. So it's true because of the transitive property applied to propositions 2 and 3. So that's a very detailed, very long-winded way of proving that this is equivalent to that. But it has the style of a proof, and we're going to come back to proofs and spend a lot more time looking at them and practicing with them and getting really good at this. But this is kind of a first foray into it. But just for kicks, is there a different way we could have proven this that might have been a little easier? Something from Engineering 250?
Truth tables.
Truth tables. We could have proven this with a truth table.
I was wondering about that.
Yeah, and P and Q, there's 2 variables, there's 4 possibilities for their truth values. You figure out what this looks like, you figure out what that looks like, show that they're always the same. So in this case, we could have done a truth table, but we're going to find other things that we're proving where a truth table might involve a few million rows, but a proof done like this might be, 5 or 6 statements. Truth tables are nice because they're very easy for computers to do, and they're very kind of mechanical. That's why they're easy for computers. They're very mechanical. You list all the possible values of the different variables, you do the calculation of both of these, and you show that they're the same. But it doesn't always work. If you have lots of propositional variables, your truth table gets very long. Alright, so we'll come back to proofs in a while, probably next week. But let's switch gears again and let's look at more propositions derived from other propositions. So we're going to talk about something called quantifiers. And there's 2 quantifiers we're going to use. There's something called the universal quantifier. And this is roughly equivalent to the statement for all. And we write the universal quantifier as an upside down A. And so, for example, we could make a statement for all x is bigger than 0, or x is equal to negative absolute value of x. That is a proposition. and it says for all numbers x, and we're assuming x is, you know, a number, an integer maybe. For all x, x is bigger than 0, or x is equal to the negative of its absolute value. Well, that turns out to be a true proposition. Because if x is bigger than 0, this is certainly true. If x is a negative number, like negative 10, its absolute value would be 10. Negative 10 would be negative 10. That's true. And if x is 0, then absolute value is 0, and 0 is equal to negative 0. So this is a proposition that's always true. But it's a proposition that says for all x, this is true. Here's another proposition that's true. For all x, x squared is bigger than or equal to 0. Well, if we're working over the integers, this is absolutely true. If we're working over real numbers, this is true. If we're working over the complex numbers, this is not true. Because if x was the complex number I, its square would be negative 1. So more cautiously, we might write for all x contained in z, x squared is bigger than 0. And now we know we're talking about all numbers that are an integer, and yeah, the square of every integer is bigger than or equal to 0. Alright, and then there's the existential quantifier. Which says there exists, and we write that as a backwards E. So there exists an x such that x squared equals 4. Well, that's true. In fact, there's two x's, positive 2 and negative 2. This is the proposition, there exists an x such that x squared equals 2. Is that true or false? I don't know. It depends where these x's come from. So if I wanted to be more precise, I could say there exists an x contained in z such that x squared equals 2. Well, that's a false proposition. There is no integer whose square is equal to 2. But if I say there exists an x contained in the reals such that x squared equals 2, well, that's a true proposition. So the universe of discourse will come into play here. When we say there exists an x, or for all x, we need to know what the family, the universe of possible x's are. So you got to specify what that universe is. Alright, well, this comes into play in propositional logic when we talk about families of propositions. So we can create a family of propositions. For example, let P of n be the proposition n plus 1 squared equals 2n plus 1 plus n squared. And I would specify what n could come from. So for example, let's say n is contained in the set of integers. Well, since n can be any integer, I've got a whole slew of propositions here. In fact, I have an infinite number of propositions. So P of 1 is the proposition 1 plus 1 squared equals 2 times 1 plus 1 plus 1 squared. P of 17 is the proposition 17 plus 1 squared equals 2 times 17 plus 1 plus 17 squared. I'm describing a whole set of propositions using this one statement. but I've got, you know, a variable here, some kind of wildcard in the name of this proposition. So this is like an array of propositions, if you like. Right? P17 is a proposition, P1 is a proposition, P5 is a proposition. They're each different propositions. And so we could say something like, you know, for all n contained in Z, P of n is true. This is the claim that for all integers n plus 1 squared is equal to 2n plus 1 plus n squared. Well, that is true. So let W of n be the proposition W squared equals W. So the proposition for all n, W of n, that is false. Let's say for all n contained in Z. Right? It's not true that for all n contained in Z, I'm messing up here, n squared equals n. It's not true that for all n contained in Z, n squared is equal to n. 5 squared is not equal to 5. So this is false. But if we say there exists an n contained in Z, such that Wn, this is true. In fact, there are two values of n in the set of integers for which W of n is true. W of 0 is the proposition 0 squared equals 0. Well, that's true. W1 is the proposition 1 squared equals 1. That's true. W2 is the proposition 2 squared equals 2. That's false. W3 is false. W4 is false. Most of these propositions are false. But there do exist at least one n for which Wn is true. So this is the proposition that there is at least one n for which this is true. All right, so we're going to continue with that on Wednesday, but let's take a quick look at the homework, and let's see how much of this we're in good shape to have you tackle. Come on, Canvas, there we go. Let's take a look at homework 2. So chapter 1, section 1.5, you should be fine doing those. Let's take a look at chapter 3. So 3.1, section 2, or question 2. So 3.1 question 2 is saying for the following propositions, identify simple propositions and express the compound proposition in symbolic form and determine whether it's true or false. So for example, the world is flat or 0 is an even integer. So that itself is a proposition, but it's actually a disjunction of two other propositions. So what you want to do here is define a proposition. Let W be the proposition the world is flat. Let Z be the proposition 0 is an even integer, which it is, by the way, it's divisible by 2. And then you could rewrite this expression, this compound proposition, as W or Z, you know, with the V symbol. So this is an exercise in taking these more complex expressions, things that have ands and ors in them, and defining propositional variables for the subparts of them, and then writing this compound expression in terms of those subparts using, you know, the symbology of propositional logic that we've been talking about. And then it just wants you to state whether these propositions are true or false. So that's question 2, 3.1. 3.2, question 2. Let's see what we got to do there. This is constructing truth tables. So you should definitely be able to do this because we've gone over the truth tables and the behavior of conjunction, disjunction, and negation. So these are exercises in constructing truth tables. So that should be fine. And then 3.3, numbers 2, 4, and 6. So question 2, construct the truth table for this proposition. And then give an example other than x of a proposition generated by P, Q, and R that's equivalent to x. So do some sort of manipulation on here to come up with another expression that's equivalent to this. But they ask you not just to say, you know, x is equivalent to this, because we know that this is what x is. But do some sort of manipulation, use some kind of identity rule or rules to come up with an equivalent. All right, give an example of a proposition that implies x. In other words, find me a new proposition, Q, such that Q implies x. In other words, not Q, W. Give me a proposition W, so that if W is true, then x is true. In other words, find a proposition W such that W implies x. If W, then x. And then for part D, give an example of a proposition implied by x. So find me another proposition Z such that this is always true. But don't just, you know, rewrite x, because I know x implies x. If x is true, then x is true. Try to find some other expression different from x, which is guaranteed to be true if x is true. Again, these are trial and error, right? The goal is to get more familiar with propositions, implications, that kind of thing, and you're doing it by way of these exercises. Well, these exercises, there's no algorithm in the book. If you want to find an expression implied by x, here's what you do. You're not going to find that. Now, if you go online, you'll find it, but then you don't get to learn what you're trying to learn, right? So you got to play around with these. And you know, if you can't do it for this x, make a simpler x. Suppose x is just r and p. Can you find an expression that this implies? Can you find some expression z that's true if r and p is true? So mess around with those. Office hours are always a good option too. Alright, suppose that x is a proposition generated by p, q, and r that's equivalent to p or not q right out of the truth table for x. So x is a truth table, x is a proposition containing 3 variables, p, q, and r, but it's logically equivalent to this, so write out the truth table. So it should have 8 rows for the 8 combinations of p, q, and r. And then question 6, find a proposition equivalent to p or q that uses only conjunction and negation. In other words, we've got a disjunction of p and q here. Find an equivalent expression that uses only conjunction and negation. And that should be doable. And then let's go back and take a quick look at the chapter 1 questions. So, chapter 1, section 1.5. So let me get to those. So questions 2, 4, and 10. So question 2, calculate the following series. So these are summation questions. And there's a note here, right? My note says for A, C, and D, there are 4 questions. For 2A, write out the answer for n equals 1. Then write out the answer for n equals 2, and then n equals 3, and then n equals 4. In other words, this is saying, you know, suppose n equals 1, what is this expression equal to? This sum from k equals 1 to 3 divided to the n. For n equals 2, what is this expression equal to? So you're going to have 4 answers for part A. You're going to have 1 answer for part B, 5 answers for C, 5 answers for D. Let's see, n equals 1, 2, 3,
Looks like 4 to me.
4, 4, 4, and 1. Yeah, so a total of 13 answers. So 4 answers here, 1 here, 4 here, 4 here. Thanks, I can't count.
Is that first I supposed to be a K? Sorry.
So, there's a typo in 2A. It should be the sum for I equals 1 to 3, not K. So yeah, that's a typo.
Okay.
So you, always on the homework, make sure you look in Canvas. It's not clear how you'd know which problems to do anyway, but I usually put clarifying notes in Canvas.
Okay, so does that mean that, are we just treating I as a random number, or are we treating it as the square root of -1?
I is a placeholder for this summation. It's the same I here, so it's like for I equals 1 to 3. So no, it's not the square root of -1. It's just a placeholder for this summation calculation. All right, and then question 4 is asking you to verify the following properties for n equals 3. So we said that you know, if you take the summation of two things added together, it's the same as taking the individual summations and adding them. And that's a tricky thing to prove. We don't have the machinery for that yet. But if we pick one particular value of n, this statement says the sum from I equals 1 to 3 of this expression is equal to this sum from 1 to 3 plus this sum from 1 to 3. And that you can actually show. And you can do it just using properties of arithmetic, commutivity and distribution. And the same thing for part B. So it may feel really obvious what you do here, and that probably means you're doing the right thing. So for question 4, right, think about what these equalities mean. They may seem obvious, which can make it harder to prove because it's like, well, it's obvious, right? So try to get below that surface level knee-jerk of like, well, obviously this is the same as that. Think about how you would actually show that. And then question 10 is the last one. So the pi symbol is a product. It's like a sum with a sigma, but you multiply the terms instead of adding them. So 2 to the 0 times 2 to the 1 times 2 to the 2 times 2 to the 3. So go ahead and evaluate this. This one, part B, this can be done without too much work if you think carefully about what it means. I want a number or a fraction for an answer here, right? I want a number up here for the answer for 10A. I want a number for 10B. You can leave it as, you know, something over something. It's just a simple fraction if you want. But don't multiply 100 fractions together to get this, even though that's what this means. Think about it, write out a few terms, scratch your head, and see if you can find a simpler way to express the answer for 10B. Alright, so that's the homework due on Wednesday. We've gone through everything you need to do that. Unfortunately, we don't have a class meeting before the homework's due because we're twice a week and we miss Monday. So plan to come into office hours either tomorrow morning or Tuesday morning, or both, if you have questions on this. So I would say look this over. If something's not at all clear, come by office tomorrow. Otherwise, work on it, plan on having it done by Tuesday, and come by office hours Tuesday morning if there's questions. Alright, we're over time. Thanks for sticking with me. Have a great afternoon, and I will see everybody next time, next week. Have a good one.